Now, very delighted to introduce our speaker today, Fabian Ruehle. Fabian studied physics and computer science and received his PhD in theoretical physics from the University of Bonn. He was a postdoctoral fellow at DESY Hamburg, the University of Oxford, and CERN. Since 2021, he has been at Northeastern University with appointments in both the Department of Physics and the Department of Mathematics. And he is also a senior investigator in the NSF AI Institute for Artificial Intelligence and Fundamental Interactions, which is a virtual institute comprising the Boston-based universities of Harvard, MIT, Northeastern, and Tufts. His research focuses on developing machine learning methods that yield exact, rigorous results for applications in theoretical physics and pure mathematics. So please join me in welcoming Fabian for today's talk, which is titled Symbolic Regression, Sparsification, and Kolmogorov-Arnold Networks. Fabian, I'll hand it over to you next.
All right. Well, yeah, thank you very much for inviting me to talk here at First Principles. Thank you all for joining. I'm very excited to be here. And yeah, in the next hour, I want to talk about my research. And the way I set this up, as you just heard in the introduction, I have a background in computer science and in physics. And now I'm doing a lot of math and physics. So I've been really thinking about ways in which I can sort of bring AI into formal aspects of theoretical physics and mathematics for almost 8 years now. I want to talk about one specific aspect of this in a little bit more depth, but I want to start out with a little bit broader. So I hope you allow me for the first 3 slides to sort of cast a little bit of a wider net, tell you sort of different ways in which I think and I have been thinking about making this useful. And by this, I mean sort of AI techniques for these more formal areas. And then I will give you sort of a deep dive into the title of my talk about symbolic regression, sparsification, and Kolmogorov-Arnold networks. And what I'm presenting here is work that I've been doing mostly with collaborators from IFI, and it appeared in these 2 papers, as well as some work in progress, which I'm excited about and which will probably appear in the next few months. Okay. So I think it's fair to say that compared to some of my colleagues in the more experimental scientists, theoretical physics and pure mathematics have been some sort of late adopters of machine learning techniques, and they are still in the process of adopting it. And if you ask why that is, I think sort of there are a few answers that are pretty clear why we have been lacking behind our colleagues in some of these areas. And the reason is there are some challenges that sort of we as theoretical physicists or mathematicians have to meet that are unique to our field. And one of them, or perhaps the biggest one, is that neural networks are notoriously black box. So they are extremely difficult to interpret. And that is not just like one particular reason why that is, but there are many reasons actually that make this hard to interpret. One is that very practical reason. If you have a billion or trillion parameters, it's very, very difficult to sort of just look at that and say what any specific parameter would do. So they are just too large. The second problem is they were somewhat modeled after the human brain. That's why they're called neural networks. But some of the human brain is not very good at comprehending the way that these things are written down as deep sort of deep compositions of affine maps and nonlinear maps and affine maps. This is not how we typically understand functions as a human. We understand functions, in terms of, I don't know, a Fourier series or in terms of a Taylor expansion or something. We're not used to looking at this in this way. So it's very hard for us to visualize what it actually is that the neural network is doing. Third, neurons are polysemantic, meaning if you look at sort of which neuron fires when you ask an LLM, let's say, to do a specific task, you will see sort of the same neuron fire on, I don't know, when you ask it to write a poem, when you ask it to write C++ code, or when you ask it to translate, I don't know, German to English. So it's very, very difficult to say what this neuron is actually doing because it's not doing just a single thing. And more abstract concepts are also distributed across activation patterns. So sometimes you cannot even pinpoint the one neuron that is doing something, but it's a more delocalized problem. And this is also sort of the next point. If you have these dense layers in your neural network, they introduce non-local effects, meaning that if you change one small change to one weight, it will sort of change the entire network down the line because of the fully connectedness. So it's not that you can do some local change here, some local tweak here, and it will lead to some local tweak there, but somehow you need to comprehend the entire forward process from that point onwards in order to interpret it, in order to see what is going on. And lastly, neural networks are a function parameterization, so they are a class of functions, but many different parameters can actually express the same function. So again, there's this redundancy which makes the function look different, or at least the parameters look different, but in the end, the function is functionally the same. And this again hinders sort of understanding of what is actually going on. So this is all just sort of a collection of issues that I identify why neural networks are actually black box. There are more, but at least these ones are the ones where I might have some idea of what you can do about that. The second bigger point is that neural networks are also stochastic, which means that even the process of finding the algorithm involves a bunch of arbitrary choices, like the neural network architecture, the hyperparameters that go into your training. All of these things are just, you cannot really find them from first principles. We lack a deeper theory, so you just sort of randomly choose something, and then your network is randomly initialized, and then it finds a random function, and the output is probabilistic in this sense. However, if you do a sort of science, exact science is like theoretical physics, you want to have sort of exact results that are not stochastic in any way, that are just sort of the answer is the answer, and you don't have any room for the stochasticity. The third big problem is that they are error prone, meaning they can make mistakes. They do make mistakes. And of course, everybody who used a large language model had it lie to you at some point. And these mistakes are extremely hard to quantify, or they're even very, very hard to detect. So when I ask ChatGPT to explain some concept that I'm new to and unfamiliar, it's very, very difficult to see where it lied to me or where it even went wrong. So the question is somehow, can we take that out of the equation? Which will again be very, very important if you want to use it for more formal aspects, where you need to be sure, 100% sure, that a mathematical proof or a physical derivation is correct. So the first 3 points somehow are all linked together. They have to do with sort of stochasticity, errors, and us not being able to really fully understand what is going on in the neural network. The fourth point is slightly different. This has more to do with the training process itself. So the problem there is that scientific papers typically are not written in a way that is particularly suitable or helpful for training large language models. If you write a paper and you think about sort of how you performed the research that led to this paper, it's completely different from what you actually write down in a paper. And the problem there is that it has been shown that, for example, for LLM to work in the context of AI safety or so, it's actually helpful for the neural network to see negative examples, to see failures, to see mistakes, and then so that it knows what it shouldn't do, and then you train it or tune it to do only the things that you want it to do. But this is completely not how we write papers. So these 4 things sort of present challenges in my mind to applying neural networks to these formal questions in science. And in the rest of the talk, I want to sort of go through these points and say a few things that I've thought about what we can do about them. And today's talk will mostly be focused on the first point, a little bit also on the second. But I also want to say quickly something about points 4 and 3. So what I will do next in my motivation, I will go backwards, say 1 sentence or 1 slide about problem 4, 1 slide about problem 3, and then I will, for the remainder of the talk, I will focus on sort of the black boxness and what we can do about that, and sort of these subpoints that come with it. Okay. So for the large language model training, sorry, that's a typo, that should be training. as we just discussed, sort of they are written in a way that is not how we actually found things. So typically when you work out a theory or when we work on a model, we take detours, we try out different things. We have a lot of failure modes. Sort of sometimes we come at it backwards somewhere. Sometimes we set out to solve something else and sort of diverge to solving this other problem that we found on the way. And none of that is reflected in papers. So we got together with different colleagues here from industry and other universities to think about sort of what would it take to set up papers in a way that makes them actually more trainable for large language models. Can we somehow develop tools and techniques that would help to train a neural network actually based on the scientific method and the scientific process, rather than sort of just feeding it papers and it only ever seeing sort of results in a linear sequential order, rather than sort of just prove theorem without seeing any failure modes. So this was the point of this paper. As I said, this is not the topic of this talk, but I think it's an interesting question, and it's a question that we should think about. So I wanted to mention it briefly here. Point 3 was about error proneness. And so you might ask yourself, what can I do to actually prevent errors completely? And it's clear that sort of just natural language won't do that. Natural language is always to a certain sense imprecise, and it always allows you to sort of, by not saying things or saying things in a certain way, to gaslight people or to just sort of sweep things under the rug. So recently there has been a lot of interest, especially in the more formal community, into proof auto-formalization. And there are many different languages around that do this. One that has seen a lot of interest in the math community is called Lean. And this has created a lot of interest because it's not, it's not just, I'm not meaning this in a negative way, but it's not just solving math Olympiad problems, which, are high school problems, but it's solving essentially, or it's used in Fields Medal level research. So it was used by Fields medalists like Peter Scholze and Terry Tao to formalize problems that are at the cutting edge of mathematics. And the idea of Lean is sort of, it's a language, and if it compiles, then everything that is written inside of the library of this language is self-consistent. So it's completely impossible to make an error. This sort of takes errors completely out of the equation. If something is inconsistent, this thing will not compile. Problem is that Lean is kind of tedious. That's its point. It's sort of, by construction, it's very difficult to write because you need to be very careful and explain everything, sort of define everything down to the last comma. And it's based on something called dependent type theory that makes it difficult for people who don't have training in this sort of thing. So for an average theoretical physicist or mathematician, it makes it difficult to use. But actually, sort of LLMs, especially sort of if you set them up in an agentic way, are becoming better at writing these proofs in Lean. And for areas in physics for which axiomatic approaches exist, so something like quantum mechanics, quantum field theory, quantum information, I think it's very conceivable that very soon we will be able to just use Lean or use an LLM that sort of writes Lean for you, and that sort of will be able to make statements or check correctness of statements in these areas. And I mean, if you think about quantum mechanics, mostly it's linear algebra or operator algebra. So a lot of this has already been formalized in Lean. So you can already just sort of put together the different building blocks and it should do it for you. A second way of addressing errors, and in some way also the first two challenges, are techniques that you can sort of adapt from theories that have been developed in numerical analysis. One of them is, which has seen recent results and sort of successes, has been, for example, in applying so-called physics-informed neural networks. So these are neural networks that solve partial differential equations, and then making statements about these approximate solutions which are found by the neural network being close by to a actual solution. And if you have enough control over the error that the neural network makes, you can make an exact statement nevertheless. So sometimes if it's close enough and you can prove some contraction property, you can show that there actually does exist a solution. And people have done this, for example, with Navier-Stokes or with those sort of fluid dynamic problems. However, this is very, very difficult, and it requires a case-by-case analysis. So if you want to apply this, I don't see a generalizable way forward at the moment. It seems to be very much sort of domain experts doing this in very specific cases and working very hard to get this done. The second setup is to actually use reinforcement learning. So this means essentially you give up or you embrace challenge 1, 2, so the black boxness and the stochasticity. And sometimes you might say, if I just try to sort of win a game of chess, I'm not asking how to understand the chemical processes in Magnus Carlsen's brain that sort of led him to make a certain set of moves. That's the wrong. All that I care about is sort of looking at the moves he does, and from these moves, I try to reconstruct the stages of the theory that he's applying, or I try to reconstruct, the patterns that he's recognizing on the chessboard and that he's following in order to win the game. And this we have applied at many different setups. So that's what I call gamifying science. So you turn your problem that you have in science into a game, and then you just sort of apply reinforcement learning to it, which will give you a sequence of steps that will solve the game for you. And you can just look at this sequence of steps and you can verify that each individual step is correct. And then if it solves the game, if it wins the game, it solved your problem in the end, and that's good enough. So now you have a proof which consists of the sequence that the neural network figured out, and it's verifiably correct. It has 0 error in it because you can just sort of check and verify. And you never had to understand the neural network in the process, because sort of you didn't have to understand how it came up with its decision. It could have been stochastic. When you play chess, there are many good moves you can do next. It's just sort of the thing that is important is there exists a sequence that won the game in the end. And this way of thinking is what we apply to many problems in number theory, in theoretical physics, number theory, topology, and so on. And this has been worked out in these papers. Okay, so now I'm coming actually to the main topic of the talk, and this is how we address challenges 1 and 2, so interpretability and stochasticity. So if you want a neural network that's more interpretable, we perhaps need to rethink the neural network architecture, because many things that are built in there, sort of the denseness of the connections and so on, the number of parameters, the fact that we cannot sort of comprehend this deep composition of maps, this is all already ingrained into the neural network architecture. So if you want to make good there, we perhaps need to rethink what type of neural network architectures we can use. And one proposal that I was involved in is these so-called Kolmogorov-Arnold networks, a way of then taking this neural network and making it deterministic, interpretable, and sort of less error prone is by combining this with symbolic regressions. Once you have a symbolic formula, that is a prediction that came out of your data, the neural network proposes a theory for you, and you can sort of take this formula, you can sort of test it, you can make predictions at any input, you can see whether it makes sense physically or mathematically, or just sort of what type of functions appear, whether that is a good model for what you're trying to explain with your theory. So these two ways of taking a new architecture and combining it with symbolic regression, these are the ideas that I want to sort of explain in this talk, how to get around challenges 1 and 2. So for the remainder of the talk, I want to talk about this architecture, the Kolmogorov-Arnold networks, and then I want to sort of show you how they can, or why they are actually very well suited to combine with symbolic regression. And in the very end, I want to briefly tell you about this work in progress that we have, where we try to sort of bring this back into the neural network world and sort of see how we can think of these as sparsified neural networks, in the hope that we can sort of get some of their positive properties that I will be mentioning into neural networks more generally. Okay, so the first part, Kolmogorov-Arnold networks. And the motivation for this, sorry, my screen is not updating. It says it's displaying slide 11, but I'm still on slide 10.
I can see slide 11.
Okay, good. Thank you. Now it updated.
Neural scaling laws, is that the one?
Yes, now it updated for me as well. Sorry about the hiccup. So as a motivation for why you want to do this, or for why people are doing this, yeah, the motivation for this is, of course, a double descent, which means that sort of at some point, if you put more parameters into your neural network, at some point it will start to overfit, and the test loss will diverge from the train loss, so you get this generalization gap between here and here. But then if you just vastly overparameterize your neural network, your training error is 0, but your test error goes down. And your test error actually goes down in a very predictable way. It follows this scaling law. If you either give your neural network more parameters, or if you increase the data set size, or if you throw more compute at it, all of this always sort of is linear in a log-log scale, which means it follows this, this power law decay. And sort of, if you can get this exponent very, very large, or, I mean, very negative, that means that the error goes down very, very quickly compared to the number of parameters or data set size or compute that you throw at it. So, but if you think about sort of what is going on here, why is it overfitting here and not here? So overfitting essentially means that the generalization is bad, and typically that means that it's sort of overfitting to noise, and it's sort of doing wild, crazy things in between the training points. So on the training points, the error is 0. On the test points, the error is huge. And I've plotted one example here where I just sort of took 10 points and fitted a polynomial to it. And you can find a polynomial of degree 9 that goes to 10 points. Yeah, polynomial of degree 9 has 10 parameters. You can fit these 10 parameters to go through these 10 points, and you get this yellow polynomial. But of course, this is a terrible approximation for probably what's going on. I mean, all the data here is, between 0 and 1. However, sort of this polynomial has gigantic values, 10 to the 5 here, and this is why you get this this huge generalization gap. So what you probably would want to have is something like the blue curve here. This is not overfitted. So this is sort of smoothly going through it, and it's not doing crazy things in between. And somehow this double descent phenomenon tells you, okay, if you throw a billion parameters at your model, it will go from the yellow curve to the blue curve. But if you have no idea what's going on here, and you just see this, and somebody tells you, okay, sort of instead of giving it 10 parameters, I gave it a billion. This sounds completely crazy. If you look at this, there has to be a better way of doing this. It can't be that sort of the only way is to sort of spend that much compute and throw that much parameters at it just to go to this rather smoothly looking blue curve. And of course, there are many ways of doing this. A popular one is so-called splines. If you ever took a class in numerical analysis, the first thing they tell you is to never actually do what I did here, to use a degree 10 polynomial to interpret or to interpolate these nine points. And the reason is precisely because if you have a degree 10 polynomial, that's fine, you can fit 9 points. But if you take a derivative of a degree 10 polynomial, you get a degree 9 polynomial. So that thing, has also 9 extrema, and these extrema are sort of wildly oscillating. So you have this problem of having these high degrees polynomials sort of not approximating things very well. On the other hand, if you sort of take a bunch of low degrees polynomials and you put them together, let's say a bunch of cubic polynomials that just interpolate between these 3 points here, and then the next cubic polynomial that interpolates between the next points, you get this smooth curve here, and then you don't overfit. So this has been known for a long time. So it seems like you can also prevent overfitting, at least to the extent that sort of you get this here, by just taking a bunch of low degrees polynomial and combining them that are only sort of defined in a certain data range. And that is the idea of cubic splines. And you might say, okay, that's nice and well, but how do I know that I can express my function this way? At least if I have a neural network, I have my universal approximation theorem that tells me that I can write any function as a neural network. So I'm guaranteed that the function I want to learn is at least in principle learnable by the neural network. And this is where the Kolmogorov-Arnold representation theorem comes in. So you should think of it as being the universal approximation theorem for these Kolmogorov-Arnold networks. So what they told you is if you essentially just take functions that depend on a single input, so just sort of a function from R to R, you can write any function, just like any function you like. You can write this as sort of taking just a bunch of functions from R to R and summing them all up. And then you can take another function that depends on the sum, which is again just a real number, transform this with a function and get a real output in the end. So this is the representation theorem that guarantees you can write any function as a composition of functions from R to R and sum them up. So the architecture that we have now looks like this. We have nonlinearities on the edges. On a normal neural network, you have them on the nodes. Now we have them on the edges, and on the nodes, we just sum up everything that comes in. And by doing this, we know that in the end, any function can be written in this way, so at least so that we are not losing any generality by trying this. And this has several good properties. For one, you can just look at it, and you can sort of look at these functions from R to R. These are very, very simple to visualize, and you can sort of see what the neural network is learning. And here's an example of that. This is taken from data that we generated that goes from R to the 4. So I have these 4 variables, x1, x2, x3, x4. And we produce a single output, which is given as the exponential of the sine of x1 squared plus x2 squared plus the sine of x3 squared plus x4 squared. And then if you start training this, what you will see is that it precisely learns. Sorry, I just realized this is a movie, but of course I gave you the I gave you the PDF, so I apologize. So you cannot actually see the movie now. But so what is happening is it will learn a sine here and a sine here. Sorry, it will learn a parabola here. It will learn an x1 squared here, and it will learn an x2 squared here. And all of these other connections will completely go away. So it will just sort of take x1 squared plus x2 squared and will sum them up here. This thing will become, this cubic spline will become a sine function. So now you have a sine of x1 squared plus x2 squared. And on the other side, you will also, this will become a parabola. This will become a parabola. So you sum x3 squared plus x4 squared. This will become a sine. You will sum the two sines up. This will become an exponential. You take the exponent, and that is your output. So you can just look at this at the strained Kolmogorov-Arnold network, and you can just read off what the functions actually are. So what it learned step by step. So this means this is much, much easier to visualize. It has much fewer parameters because sort of, as I explained, you don't need all of these parameters to make it not prone to overfitting. It turns out that this has less polysemantic neurons, and also it has it's much more local. It's not fully connected in the sense that it will sort of turn off all of these slightly grayed out ones, and in the end only sort of have single connections which go from x1 to a single function again into R instead of having this fully connected layer to it. It also has different behavior when it comes to the neural scaling laws. So these are empirical observations. If you look at the scaling laws that I showed you on the log-log scale, people just sort of see that it follows this. There are different explanations for why that actually is, but not a universally agreed upon theory for why that is happening. One explanation for what is going on says that the exponent is actually given by the dimensionality of the input data manifold. So this is something that you typically don't have any control over. This is just given by your problem. Also, I mean, in practice, this is not a terribly well-defined notion to begin with. If you ask yourself, what is the dimension of the data manifold of all cat images in the space of all images, or in the space of all pixels, this is not a well-defined question, because if I have some cat image and I perturb a pixel a little bit, I will certainly still get a cat image. But in mathematical notion, actually, you can very well define this. Typically, your input manifolds are sometimes actual manifolds, or they are in this case with mathematical formulae where you have sort of x and y, which are independent parameters. So in this case, input certainly is two-dimensional. X and y just take any real value, and your output is one-dimensional. And if you then take this the scaling law that proposes that the error should be proportional to the input manifold is two-dimensional, which means that in this case, the error should go down like 1 over n squared if you increase the number of parameters. And we did this for different neural networks here, and you can see they initially follow this n squared scaling law, and then sort of they flatten out. For CAN, the scaling law works completely different. In some sense, it never sees all of the input at once. Yeah, if you look at this function here only sees, every function always only sees a single input. So it doesn't even know about the dimensionality of the input manifold at this level, which suggests it shouldn't really depend on it. And indeed, we showed in the paper that the scaling only depends on the degree of the spline that you use, which for cubic spline is n+1, so it would go like n to the -4 for cubic spline, or n to the -5 for degree 4 spline, and so on. And you can see that the CAN, which is this blue line, actually also follows this very well over several orders of magnitude here. And then you can push this to the more extreme. So here we wrote a function with 100 parameters. This function has a 100-dimensional input manifold. This means that the scaling of a neural network should go like n to the -0.04. So this number is tiny. This means that the improvement is very, very, very slow. And that's, of course, not what you want to see. Whereas for the CAN, again, it doesn't matter. The CAN still has n to the -4 scaling. And you see initially it follows this, then again, so if it stops, but the error is already 3 orders of magnitude lower than it was for trying to learn this function with a neural network. So the scaling law behavior is much, much better because it doesn't really depend on the dimensionality of the input manifold. That's one good thing. Another good thing is it doesn't suffer from something that's called catastrophic forgetting, which has to do again with the fact that things are more local because not everything is fully connected. Your function itself is split into sort of its cubic splines that are only non-zero between 2 or 3 points, and then sort of the next cubic spline takes over. So I can change the first cubic spline without having to change the 17th cubic spline by much. So what this catastrophic forgetting is if you train a MLP, let's say, I have this continuous data, but initially I only have access to this first training point. You train your MLP and it will learn to reproduce this, but then sort of outside of the training domain, of course, it will, out of distribution, it will make any predictions, which is this thing here. Then I train it just with the second amount of data, and it will also learn this, but it will forget what it learned about the first data here. So you see that it now can do the second peak, but it cannot do the first peak anymore. And then I train with the third peak, and then I can do the third peak, but it can't do the first or second peak anymore, and so on. So when you continue, it forgets what it learned before, because sort of in order to make it fit the third peak, since everything is fully connected and nothing is localized anywhere, it needs to change the entire function. And this means that it overrides what it learned previously. If you do this with a CAN, on the other hand, you see that so if I learn the first peak, that's fine. I learn the second peak, the first peak is completely untouched because I have this locality behavior. Then I learn the third peak and the first two remain untouched. So because everything is localized, I don't have to change the first peak in order to sort of learn the third peak. So that is the idea here. So the locality is imposed by making the CAN sort of depend on functions with compact support, meaning functions that are only defined in a very, very small range. And also nothing is fully connected, which also makes it more local. So that's what I wanted to say about CANs themselves. If you want to try them out, you can go to the GitHub page of my collaborator who uploaded it to there, and you can just sort of download it and play with it and see whether it works for the scientific problem that you have in mind. So that is the end of the first part of my talk, where I wanted to talk about this new architecture and how it has sort of locality built in and interpretability built in, fewer parameters built in, which makes it more suitable for scientific discovery. The next part will be how I can sort of combine this with large language models in order to do symbolic regression. But before I go there, because I will be heavily using these cans. So before I go there, I want to pause here and see whether there are any questions at this point.
Amazing. So if you do have questions, now is obviously a great time to ask them. There is a little button at the top next to volume and people where you can raise a hand, and then I can call on you for questions. So we can work through some of the hands that I already see up. Matthias, why don't you go for the first question?
Hi, thank you so much for the great talk. Very interesting. My question is, I like this idea of the CAN networks for symbolic regression, but my experience with different SR algorithms is that if we try to achieve for accuracy, we end up paying with complexity. So the equations at the end of the day end up being very complex. What do you think of regularization techniques that would keep the equations simple? And the idea would be the idea of parsimony.
Mm-hmm. Yes, thank you very much. That's a very good point. I will explain a little bit how we simplify these complex expressions that we get. I will explain this in the second part. So please ask again. I won't answer now because I will go into detail into this in the second part. Just for cans, we have different regularization built in. We have entropy regularization built in and sort of edge scores that allows us to further trim edges if their activation is small. So we have several things of regularizing the can itself already, and then sort of we have simplification steps that makes the symbolic function easier. So thank you very much. It's a very good question. It's a very important question, and we thought about it, and I'll hopefully answer it in part 2.
Great, thank you.
Awesome. And then I see one more question. Judas, you can come off and ask away.
Hi, Fabian. Thank you very much for the talk. So I have a question about splines and transcendental functions. So my question is, how can a spline represent something like sine or exponential?
Yeah, very good. Yeah, so in order to represent a sine function, so what you would do is you would approximate your smooth sine wave. You would approximate it with a small cubic polynomial. So yeah, so your continuous sine wave, you have a grid on which you discretize it. Let's say between 0 and 2 pi, you put 10 grid points, and then you put cubic functions that go through 3 points at a time of the sine, and you build it up sort of piece by piece from these smaller cubic functions.
Okay, makes sense. Thank you.
Yeah, thank you for the clarifying question. Yeah, I forgot I had this GIF in here that wouldn't play on the PDF, so I apologize for this. Otherwise, you would have seen it nicely. I apologize.
No, not to worry. I don't see any other hands up for now, so I think you're good to keep going through into the second section of the talk.
Yes, thank you very much. Yeah, so now the question is, we can, as I said, we can look at cans and we can sort of see what they learned, but of course we somehow want to automate this. And this is what this LimLex package is about. So this is learning expressions with large language models using Kolmogorov-Arnold networks. And the idea is to use something that is very much like a fun search from Google, if you're familiar with this. So the idea is in fun searches, you get interpretable machine learning by just asking the LLM to write the code of the algorithm. And then you can read in plain English or in Python, you can just sort of read the algorithm that it uses. And that is, of course, very much interpretable. You just see what it does. And what you then do is you pair this with a genetic algorithm. So meaning you have the different algorithm, you ask the neural network, you ask the LLM to write, I don't know, 10 computer codes that solve your problem. You run them on the test set, you see which one works best. You show it again, says, if I have this algorithm to solve this problem, but can you improve it? Can you make it even better? And then it keeps sort of iterating on its own code until it found something that hopefully works very, very well. And we want to do the same with cans. So what we do is we show it the function that the Khan learns. So let's say here this would be a sine function, this would be an x squared function. We show it. These really just a graph of these functions, and since it's a Khan, it's always from R to R, so I can always plot this. I plot all of the splines. I show it to the Khan and I ask it, what is this? Sorry, I show it to the LLM and I ask the LLM, what is this function? Give me 5 ansatz for this function. And look at this and say, okay, this looks like a sine. This looks like an x squared, could be x4 maybe. This looks like an exponential, could also be, I don't know, x squared or something. So it will give you a bunch of ansätze. You just fit your data with these ansätze and you ask it to self-improve its ansätze. So you score them and you ask it to improve until you have converged to something that fits very well. Once you have that, and now I come back to the question that was asked previously, you get a complicated answer, and then you need to simplify this somehow. And the way we simplify the symbolic ansatz that we have is, again, we can just feed it to ChatGPT. We ask it sort of, we have this complicated function, can you simplify it for me? Or you can use commercial simplific algebraic computer algebra systems like Mathematica, or you can use Python's simpy function to just simplify this as much as possible. And then at some point, sort of you accept the result that you got and then try to move forward from that. So the crucial point here is really that sort of, I know this pun is overused, so I'm somewhat hesitant of even putting it, but it's actually true. Univariance is all you need. It is true that you can write any function as sort of functions from just R to R using the Kolmogorov-Arnold representation theorem. And by leveraging this, that we can write everything just as composition of functions from R to R, this allows us to just sort of plot these splines, these functions from R to R, feed them to a vision transformer or to ChatGPT essentially, and just ask it, what is this function? Give me an ansatz for this function. So that makes it very, very simple. And the big advantage is, compared to maybe other packages, I don't need to specify a function basis. So ChatGPT will have essentially all the functions that it has ever seen, that it has been trained with. And if you prime the neural network, let's say I tell it, I have this data set which came from cosmology. This will automatically fit a function to it. So now it will automatically sort of start looking in functions that it has seen in the context of cosmology to propose sample solutions or sample ansätze for the different splines that are in my Kolmogorov-Arnold network. So in detail, the pipeline works like this. I start with some Khan that is too big, as was pointed out in the question. I would train it and then I would prune it. So I would start with something that has 2 inputs, 4 intermediate layers here, 4 intermediate layers here, and sorry, 4 intermediate nodes here, 4 intermediate nodes here, and a single output. And the Khan package already sort of can train this, and then they can prune the ones that are sort of very, very weakly activated. You can just throw them away and you will find something like this. And then you can look at this, and if you're sort of just asking your network, what is this or what is this? And it will just say this is a linear function. So good, for a linear function, I don't need an extra layer, so you can prune away this layer. And then in the end, what you get is this ansatz for the decomposition of the function. And in this case, if you just look at it, sort of here, it's not so obvious, but if you sort of put numbers on the axis, you see that this is a log, this is a log, and this is an exponential. So what it is doing is it's taking the log of x plus the log of y, and then taking the exponential. So if you simplify this with your exponential laws, this is just x times y. So this neural network learned x times y. And the way you would see this is, well, you ask it for ansätze for the first function that will return something like a log x plus a0 log x plus a1. You ask it for ansatz for the second function. It will return b log y plus b1. And then you ask it for ansatz for the third function. It will return c exponential c0 times the exponential of c1z. Then you fit these a, b, c coefficients, and you get some numerical values here. And so you can immediately see that sort of, since I'm just summing up this plus this in the first node, A1 and B1 are sort of overparameterizations of the problem, because they will just sort of, the problem in the end doesn't depend on A1 and B1 individually, it just depends on their sum. So you have this problem that I mentioned earlier, that you have sort of different neural networks that express the same function. You also have this here, but cans give you a way of simplifying this away. So meaning now we just put everything together according to the computational graph that the can gave us. So as I said, so we take A log X plus plus A naught, we take B log Y plus B naught, and then we multiply that all by C as we are instructed here, and we get this function. Then you can simplify this using, as I said, Mathematica, or just asking ChatGPT, and it will simplify it to this. And then if you put in numerical values, you will see that C naught is actually the inverse of this factor. So this just simplifies to E log X plus log Y. Then you feed this again to ChatGPT, ask it to simplify this further, or you feed it again to Mathematica. And in this case, what ChatGPT will give, if you give it this function, it will tell you, well, this, I asked it to give me 10 different ansatz, and it gave me X times Y, Y times X, X times Y plus 0, X times Y without a space. So you see, it essentially just gave me X times Y for that, and gave me 10 different variations of that, because I asked it to give me 10 different ansatz. So now there was this redundancy, there was this sort of additional complication in the ansatz, but we were successfully able to simplify it away using symbolic methods as well as AI, in this case, sort of ChatGPT. And again, if you want to, you can try this out yourself. It's on the GitHub of my collaborator. Just download it. We have a bunch of test cases where we applied it to all sorts of functions, and hopefully it will be useful for your function as well. For the final part of my talk, I quickly want to talk about how we can think of cans as sparsified neural networks. And no, the slide is not advancing again.
I see the next slide, cans as NNs, so it may just be like a little delay on your end.
Yeah, I think it's on my end. Yeah, okay, so now I see it. Yeah, so the idea is you can think of a can as a specifically sparsified neural network. And so what I drew on the left is a fully connected neural network. I already sort of wrote this somewhat suggestively. And what I drew on the right is the corresponding can. And well, one way of seeing it is you cut most of the connections here. So first of all, I single out these points here as these points here. And then I cut most of the connections. So I sparsify, make this not dense, but very, very sparse, until I end up with something that roughly looks like this, where now essentially I just have the input from here to the hidden layer. This just goes to these 3 nodes, and these 3 nodes now sort of learn this function here. Or if you wanted to, in the other directions, maybe even easier to see, instead of putting splines here, I could put small neural networks here from R to R that learn these functions that I plotted there. And of course, this neural network is a very, very special sparsified version of the full neural network I had in the first place. I've cut most of the weights away. And this gives me now an architecture that sort of morally looks like a can. Yeah, sorry, it's a bit slow on my end to show the next slide. Yeah, so there has been a recent paper by 2 authors where they showed that if you train a neural network, it actually, in the many circumstances, canifies itself. So meaning it does this sparsification here that we just did by hand. It also does this during training. It tends to turn off certain weights. It does something that's called minor concentration, where it sort of turns off all of the weights and makes the neural network by itself more can-like. And that begs then the question again, do we even need these parameters, or can we sparsify from the very beginning? Can we build in that this can-like structure does good things with its locality, like fighting catastrophic forgetting, has better scaling laws? Can we sort of achieve all of this if we just sort of sparsify by hand? And if we could, that would of course be very, very useful. We know for a fact that we don't need all of these parameters. We know that we can prune neural networks. We can throw away, after training, we can throw away 99% of the or 95% of the weights, and you will still get a decently performing neural network in most cases. But if you try to sparsify from the beginning, typically the neural network doesn't learn at all, or so if it lands in a completely different minimum, that is not generalizing very well. So that is the problem of sparsification. And of course, if you could sparsify from the beginning, you could save yourself a lot of compute cost, time, power, because you would have just a small fraction of the weights that you actually know you will need for the final function. So we tried this idea, as this is work in progress, so there's nothing really definite at the moment, but what we did is we took a very simple data set. I think this is for SciFar or MNIST here. And we took a neural network, made it very, very big, and then we sparsified it in the way that I just showed you by cutting all of these extra edges and turn it slowly into a can. And this is measured on this x-axis here. So the sparsity of 0 means it's the full neural network. Sparsity of 1 means, or almost 1 means it is a can now. So I'm throwing away connections, more and more connections that make it look more and more like a can. And what I show in this plot is what happens if I sort of throw away the same amount of weights, but I'm not turning it into a can, I'm just throwing away these weights randomly. And you see that sort of up to sparsification of 95%, the neural network learns this data set, and then it very, very sharply drops. And the accuracy of goes down to less than 40% in this case, when I reach as many parameters as I have in the can. Whereas if I take a neural network that has been sort of canified in the way that I showed before, I will get, at the same parameter count, I will get something like 81% accuracy. Whereas if I do it randomly, I get less than 40. So from this very initial data point, it seems like, yes, canification, so sparsification to turn a neural network into something that looks like more like a can actually is feasible. And compared to sort of random sparsification, it will actually perform much better, and it will still learn sort of the essence of the function without dropping off sharply here. So that's a promising first indication that this might work, but as I said, it's work in progress. We need to test this much more. That's the last thing I wanted to mention here about sparsification and localization. So let me just conclude. I tried to convince you that machine learning for theoretical physics has its challenges. And one way of overcoming these challenges is perhaps with new architectures. CANs is one proposal for that. It has fewer parameters. It has better visualization. It's more localized because it's sparse and the splines are compact supported. It has better neural scaling laws. Its univariance is actually very well suited for multivariate symbolic regression, because even if you have a 10-dimensional input, you're writing your function always just as a function from one of these 10 inputs into R. So you can visualize this on every input coordinate or on every feature and feed this to an LLM, whereas sort of course, you couldn't plot this. You couldn't sort of feed the LLM a plot of this 10-dimensional space. And lastly, we have preliminary indication that sort of this can-like structure actually sort of, if you sparsify a neural network to look like a can, is a possible or feasible way of doing it of writing it down a neural network which has much fewer parameters. So we hope this bears out in more examples in the future. And with that, I conclude. I'm happy to take more questions, and I want to thank you very much for your attention.